This is the Unit 6 Electric Circuits review for the final exam for Physics 12. And again, we're still working off of our tutorial package. And we're on this page here. I'm actually going to go down to the bottom of this page and just kind of talk about the tools that we've got for doing questions with electric circuits. So I'm just going to stick some stuff in a box here. And I'm going to actually put a little bit more stuff maybe in a box just over there. So there are remarkably few topics to this chapter, but then there are just a whole host of different ways that you can use them. But really, as far as electric circuits go, we've only got three main tools that we use all the time. We just keep using these same tools over and over and over again. One of them is Ohm's law. And so this is the law that relates current to voltage. We know that the current that you're going to get in a circuit is the voltage that you apply divided by the resistance of that part of the circuit. Another tool that we use a lot is the idea of current junctions. That the current into a junction in total has to equal the current out. So sometimes called the junction law, sometimes called the current law. And the third tool that we use a lot are voltage loops, sometimes called the voltage law, sometimes called the loop law. And that says if you go all the way around a loop, then the voltage gain has to equal the voltage lost. There's some calculations that we're going to do in the review here involving power. And we've actually got three choices for power. Your classic is to go I times V, but there are a few other variants. You can go I squared R, and we could also, oops, little mistake there, we can also find power by going V squared divided by R. So we're going to be using those three main tools through most of this. We'll look at some extra stuff on the next page, but for the most of the stuff we're going to do here, those are the main tools. So back up at the top, got this circuit here. It's got an 80 volt battery, a couple of resistors 1 and 2, just like they're in a nice series arrangement, but then 3 and 4 are in a parallel group, and you're asked to try to find the power dissipated on just resistance 4, just the 8 ohm. We can't go and just do V squared over R with the 80 because the fourth resistor doesn't get the full 80 volts. So we got to start tearing this thing apart. And I'm going to take this section right here and I'm going to group it together as a group. And I'm going to go and find out what the total resistance of that group is. So it is in parallel. That's when you have to do the reciprocal additions. So I'm going to go 12 flipped plus 8 flipped. Add that up, flip it back. So that section alone, just that group, has a resistance of 4.8 ohms. So R on the group, 4.8. Okay, well that lets us keep going. Now if we want to, we can figure out the resistance of the entire thing. It looks like overall it's a big series circuit. So the total resistance of everything, we've got a 12, we've got a 10, and then we've got this group, this 4.8, for a grand total of 26.8 ohms for everything. Okay, well now I'm going to go and use one of my three main tools. I'm going to go and find the current flowing in the entire circuit. So IT, well that's just going to be all my voltage divided by all my resistance. So I'm going to take 80 volts, I'm going to divide it by the 26.8 ohms of resistance. And when I tried that out, I had around almost 3. It was like 2.98 amps of current flowing on the main wire. So that's flowing, if you were to draw it in on the circuit, that's flowing out of the battery and into this loop and through that resistor and through the resistor number 1 until we get back to the battery again. It's flowing overall through the group as well. And what we have to do is try to come up with some power calculations, but just on resistance 4. I'm going to do Ohm's law again, but now I'm going to do it on the group and say, you know what, as a group, that 2.98 amps has to flow through the entire group. So I'm just going to go with Ohm's law and say, you know, in that group, the current in the group is equal to the voltage that we drop across the group divided by the resistance of the group. And I know a couple of things here. I know I've got overall 2.98 amps, and I know that that voltage is what I really want to find, and the resistance of the group is 4.8 ohms. And when I tried that out, I found that the voltage on that group is 14.3. Both of those resistors will receive that exact same voltage, 14.3 volts. That's how many volts we're going to drop going across them. Now we can finish this off. The power, on resistor number 4, one option would be to take voltage drop 4, square it, and divide by resistance 4. So we could go with our 14.3, square that, divided by the resistance of 8, and we have the answer. It ends up being around 25.6 watts. So just using those tools over and over again, and using also the rules for finding resistance in series or in parallel. All right, let's try the next one out. So this one here is going to force us to work backwards through the circuit. It also again has a parallel section and then a series resistor in there, the 10 ohms for resistor number 1. Got a couple of tasks. One is going to be to find the EMF of the battery, and the other is to find the power dissipated on the internal resistance. So a couple of extra tools here on this that we can actually use. When we're doing these types of questions, one main tool that we like to use is that the terminal voltage coming out of the battery is equal to the EMF. 99 times out of 100 it is subtract. It switches around if you're charging the battery, but we're not here. Minus the total current flowing through that battery multiplied by the internal resistance, just that 0.8 ohms on the inside. Another strategy that we can bring into this is, what does Ohm's law look like? How do you calculate the total resistance in this circuit? And we talked in class about 3 different ways that you can do this. You can take absolutely all of your voltage and divide by absolutely all of the resistance that the electricity has to go through, kind of the everything calculation. Or you could do just outside work. You could take the terminal voltage getting out and divide by the resistance on the outside of the circuit, outside of the battery. Or in rare cases, you could actually talk about the voltage being lost on the inside of the battery, on that 0.8 ohms, and divide that just by the internal resistance. So 3 different options to come up with the value for I. All right, looking at this circuit, I'm noticing that middle resistor on the parallel branch, the 50 ohms there, we do actually know the R, we know the I. We can actually work with Ohm's law. V would just be the I times the R. And if you do that in this case, we find that the voltage drop on this 50 ohm resistor here, I'm going to call this voltage 3, it ends up being 7 volts. Now those are all in parallel, those 3 resistors. So if resistor number 3 has 7 volts, then resistor number 2 also has 7 volts. And resistor number 4 also has 7 volts. So you can now go and figure out how much current's going to flow on those other 2 branches. You can just go I is equal to V divided by R, so 7 divided by 33. That's going to tell me how much current I've got here. When I tried that out, I found out that current in number 2 is 0.21 amps. And the current in number 4 ends up being 0.103 amps. Okay, at this point, one technique that you could use is a junction law. You can say, hey, look, all those currents came through that junction. They must have been all traveling along the main wire before they split up, and we can figure out what our total current is on that main wire. So IT is equal to 0.21 plus 0.14 plus 0.103. And when I put all of that together, I found that the total current coming out of the battery was 0.453 amps. Okay, I'm getting somewhere now. There is, by the way, another way that you could have come up with that. You could actually do Ohm's law working with groups. If you had found the entire group resistance for those 3 resistors, the group resistance, if you do the reciprocal game, is 15.3 ohms. And you can say, okay, I've got 15.3 ohms and 7 volts. How much current's flowing through there? I want to find that out, and it ends up being 0.453 as a group. So that's an option as well to come up with the 0.453. For the next move, we're going to see if we can figure out exactly how much EMF we've got for the entire circuit. Right now, I've got 0.453 amps flowing in the entire circuit. I'm going to actually see if I can get this idea to work. I want to know the EMF. If I can work with all of the resistance, like everything, then I should be able to tie that with the 0.453 amps that I know. I've got this already. I should be able to figure out what that EMF is. So that's my plan. I'm going to see if I can get this to work. So I'm going to see if I can first find out exactly what my total resistance is for everything. So I'm going to do some reciprocating here. So 33 flipped plus 50 flipped plus 68 flipped. And we'll reciprocate back. Okay, so we've got around 15.3, 15.4 ohms of resistance for everything. And what we can do now is say, all right, that 15.3 ohms of resistance also has this number 1 resistor of 10 ohms added on to that. So let's go and add on another 10. It looks like for the entire circuit, we've got around 25.3 ohms of resistance on the outside. Now that's just on the outside. So I'm just going to write that down. Okay, so we have resistance on the outside as a total is 25, I guess it's around 0.4. Now if you want to do the resistance of everything, absolutely everything, you have to include that internal resistance that's inside the battery. It looks like 0.8 ohms. So I've got to get that in there too. So I could add on 0.8 ohms. So for the whole thing, I've got 26.1 or 26.2, depending if we want to worry about rounding or not. That's for everything. I think we're now ready to go. We can go and work with IT 0.453 is equal to the EMF which you wanted divided by the resistance of absolutely everything. So that's going to be my next calculation here. So IT is 0.453. That's equal to the EMF which we want divided by this 26.2 number. Okay, well that's going to work pretty quick. I can actually just multiply that 26.2 by 0.453. And there we go. It looks like the EMF of the battery is 11.9. Okay, so I know how strong that battery is now. There's one last thing to do. They're asking us to try to find the power dissipated on that internal resistance, and it will actually do that. It will dissipate some heat. This resistor here inside the battery, right there, it is actually going to get hot and have some wattage to it, and we're asked to try to find how many watts of heat are coming off. Well, one thing I know is that little inside resistance, although there's not a lot of resistance there, that inside resistance is right on the main wire of the battery. So any total current coming out of the battery goes right on through that resistor. So I'm going to think about my options here for calculating power, and I think a really nice easy one might be, the power on that inside resistor, it's actually just the I going through that resistor squared multiplied by the resistance of the resistor. I know both of those values on the right hand side, so power is equal to all of that current goes through the resistor, and it does have a tiny little resistance to it of 0.8. And so that power ends up being, let's find out here, 0.453 squared times 0.8. Somewhere around 0.16 watts. Yeah, that looks right, 0.16, 0.164, either of those would be fine. So this particular question actually involved these two little items of theory here that are in black, the terminal voltage equation, and just the idea of how you can calculate total current with variations of Ohm's law, whether you do everything, the outside numbers, or just the inside numbers. All right, off we go. Next page. These ones actually kind of really, to be fair, tie in with the next chapter, but the next chapter is really busy for its review, so this is a really appropriate time to bring in some of these questions with motors and their back EMF when they're running. For these ones, we're going to kind of split our page. We're going to look at what the motor's doing when it's trying to start, and then what it's doing when it's running full. So it says a refrigerator condenser motor draws a 10 amp current at startup, so that's quite a bit of current. That's when it's trying to run but hasn't got going yet, when it's attached to a 110 volt source. When it's at normal operating speed, the current is only 0.2. It's way down. Looks like it's about 50 times less. What's the back EMF when you're at that normal operating speed? So as always, I'm going to split my page up and look at the starting condition and then the running condition and see if we can work with one side, grab some information and take it across to the other. So over here I'm going to do startup, and over here I'm going to do when we're running at full speed. Okay, so the general equation for working with this, it's an Ohm's law variation. The I is going to be the effective voltage, so you've got your source voltage minus your back EMF, all divided by the resistance of the motor. But at startup, the source voltage is 0. Sorry, not the source voltage, the back EMF voltage is 0. So that simplifies things a little bit. If we were to go and throw in the information that we've got, we know that we have 10 amps at startup. We also know that we've got a 110 volt source, and then there's the resistance of the coil of the motor. So swinging that around, that's a pretty easy one to solve. Looks like the resistance of the motor has got to be 11 ohms. Now there are a couple of things that you can take with you across this line dividing startup and running. One of them is the source voltage, and the other one is the resistance of the motor. So I'm going to take this information now and I'm taking it across over to the running side. Same idea. We've got this Ohm's law variation. The I is equal to the source voltage, which won't change. That's that 110 volt source, minus any back EMF because the motor is spinning, divided by the resistance of the motor. Now I get to take those two bits of information with me. I get to take the source voltage and the resistance, and we're just looking for the back EMF. So just dropping in the numbers, they've offered this information that we've got 0.2 amps flowing when we're running. Source voltage is still 110, but we're looking for that back EMF. And then the resistance here is 11 ohms. All right, let's just see what happens here with the numbers. So 0.2 times 11, we've got 2.2, so right around 2 volts, 2.2 effectively. That's 110 minus the back EMF. Okay, so that 110, if it's going to come down to 2.2, we have to subtract around 108. So that's the answer that we're going to go with here. Okay, it's not exactly 108, right? You go through the math there, it's like 107.8. But the answers there are all trimmed down to 3 sig figs, so 108. Now the next question is very similar. It's also a motor, so we're going to do the deal where we split the page and look at startup, and we also look at it when it's running. So 120 volt DC motor, that's your source voltage, has a resistance of 5 ohms. We've got 6 amps when we're operating normally. You have to find the starting current and the back EMF. We've got a couple of things to find here. Okay, well, can't go wrong with dividing your page up. And I'm going to put information about startup over here. And when we're running full speed over on the right hand side. So again, there's really just one equation. It's an Ohm's law variation. It looks like this. The current is equal to the source voltage minus the back EMF, all divided by the resistance. But at startup, there's no back EMF. It's not behaving like a generator yet. So for startup, we're actually just trying to find how much current there is. This is just a pretty straightforward calculation. Looks like the current at startup will be your full 120 volts divided by the resistance that we've got, that 5 ohms of resistance. So that ends up being 24 amps. So it's a pretty serious amount of current there. You can already start to zero in on the answer. When we're running full blast, they wanted us to find the back EMF. No problem. Again, only really one main idea here. It's an Ohm's law variation. We've got our source voltage minus our back EMF, all divided by the resistance of the coil. So that numerator is like the effective voltage. All right, the current, when we're operating normally, is it's way down there at just 6 amps. Source voltage is 120. We are looking for that back EMF. We want to see what that number is, and the resistance is 5. Okay, now be a little careful with the numbers here. You end up with this 30 showing up, which is actually one of the wrong answers. That 30 is equal to 120 minus the back EMF, just multiplying both sides by 5. The back EMF is the number that takes 120 down to 30, so it's actually 90. But the 30 is showing up there just as a bit of a trap. That 30 is it's the effective voltage. It's the value for that numerator. It's how many volts are left, if you wish. But the back EMF taken away from the 120 is actually the 90 volts. Okay, next page. Got a circuit here with a new battery and then a used battery. Just so you know, just some bits of information here, a little bit of knowledge for you. Typically on a used battery, they usually end up with a higher value for that internal resistance. Just as the battery's reactants are consumed, you tend to end up with that situation happening. They're both 6-volt batteries though, but this one's definitely going to have a different value for its internal resistance. I'm suspecting it to be a larger one. So it's got an EMF of 6, and the internal resistance on the new one is 1, and it's replaced with a used one, also 6 volts, but I'm suspecting a higher value for that inside resistance. And they're saying that the resistance outside, the capital R, now later on is 1.75 watts. What's the internal resistance of the used battery? So we're after that little r. Okay, well, I'm going to split my page up here as I go to do this work, and I'm going to look at the new battery on one side and then the used battery on the other side of my work. And there's a couple of things that we can kind of steal and take across. One is that EMF is staying at 6, and the outside resistance, whatever it is staying the same. So just so you know where we're going, on the left side of the page, I'm going to work and see if I can calculate that value for that outside resistance. So the terminal voltage for a battery, it's equal to the EMF, which I guess is 6 here, minus the current multiplied by the internal resistance. So let's see if we can get somewhere with this. We do know that the EMF is 6 volts, and they've actually offered you the current in the first one. We should be able to figure out what kind of terminal voltage is happening here. So this isn't the only way to do this. I'll show you another little variation on this in a second, but you could go and find the terminal voltage and say, hey, we've got 6 minus a current of 0.375 and then an internal resistance of 1. So actually the terminal voltage ends up being 5.625 volts. That's how many volts make it outside the battery. Now I'm going to go and do Ohm's law outside the battery and see what I get. So I'm just going to say I is equal to V over R, but I'm going to run with outside numbers. Outside the battery, the I is 0.375, and that's going to equal the voltage outside the battery, which is 5.625, all divided by the resistance outside the battery. And so then I swing that around and I find the resistance outside the battery. So those are all outside numbers. The resistance outside the battery is 15 ohms. I wanted that. I'm taking that number and stealing it across to the other side. There is a slight variation you can do on this if you would like. It does work. You could say, oh, well, can't I go and say total current is equal to the EMF divided by all of the resistance? And the answer is sure, yeah, you can definitely do that. And if you do that, you end up saying 0.375. They told me that was the total current. That's equal to the EMF of 6 divided by absolutely all of the resistance. And if you do that, you find that the resistance of everything is 16 ohms. No surprise, because there was 1 ohm on the inside. So if you did it that way, that's actually pretty fast. You could say, well, everything there is 16 ohms. Clearly the inside is 1 ohm, they told me so. So the outside resistance is 15. That stuff in purple there kind of does all the other stuff we just did really quickly, as long as you subtract the 1 ohm. Okay, now I'm going to go and take a look at the used battery. I now know for that used battery which I suspect has a higher value for R, this thing has an outside resistance of 15 ohms. But at the moment, on this outside part over here, I don't know what the value for V is, and I don't know what the value for I is. It's a new setup. And you're trying to figure out, for this one, what that internal resistance of the used battery is. Here's one option. I'm not saying this is the only way to go, but it does work pretty nice. Why don't we go with this variation for power? Power is equal to I squared times R. And let's take a look at that outside 15 ohm resistor. We're told we've got 1.75 watts of power. The I don't know right now. It's a new circuit, but that resistance out there is 15 ohms. And if we do that, we end up with a current of 0.342 amps. You could do the same thing again and say power is equal to V squared divided by R. You could also do Ohm's law here. 1.75 is your power. Let's go and find this V squared divided by 15. And that voltage out there ends up being 5.13 volts. Again, you could do that also just with Ohm's law with just V equals IR. All right, I'm now going to go back to this main idea that terminal voltage is equal to EMF minus I times little r. I'm going to use that to find the little r. I know everything else. The terminal voltage is actually the voltage that gets outside the battery. It's the voltage from here to there. But that is exactly the voltage that we've got on that 15 ohm resistor. That's the 5.13 volts. That's equal to the EMF. Thank you for telling me that that's 6. Minus the current coming out of the battery. I know that number, 0.342. Multiplied by that outside resistance. We're done. You can just move the 6 around, divide by the negative 0.342, and you'll have it. Right? It would be this quick. We could go 5.13, subtract off the 6, and then divide by negative 0.342, and we've got the value. Okay, and it is larger than the 1 ohm we had before. So around 2.5 ohms. All right, last one is a conceptual one. It's kind of a checks and arrows question. We talked about this during class, so it's a nice little reminder of this story. It's not an easy story to figure out, but it's doable. We've got 2 identical light bulbs wired in parallel to a battery. They're equally bright. When one of the bulbs burns out, however, the other one glows brighter. That's kind of counterintuitive. The idea of parallel circuit says that shouldn't happen, that actually the current should just come down to half and the remaining light bulb should be as bright as it was before, but for some reason this one's getting brighter. So use principles of physics, stuff we learned this year, to explain why the battery causes the remaining bulb to glow more brightly. So back in grade 10 or grade 9 when we were first looking at circuits, I'm just going to say grade 10. When we were looking at it there, we would say, hey, this doesn't really make sense. Maybe you've got a 12-volt battery, and then you've got these light bulbs. I'm just going to draw them as resistors. And each of them would get the exact same voltage, 12 volts, 12 volts. And if that thing was to have one of those resistors removed, the remaining light bulb still gets 12 volts and still has the same current flowing through it. But apparently that's not the case here. So there's something new in this situation. And the issue here is all about internal resistance. It's not a wire issue. If it was about the wires being poor wires, then one light bulb would already be glowing dimmer than the other. That's not the case. So I'm just going to kind of demonstrate this with numbers. And then even though I'm using specific numbers, it's okay because I could talk about it just generally later when I was finished. So I'm going to go with this. I'm going to say I've got a 12-volt battery. And I'm going to put an internal resistance in here. Let's go with 2 ohms. And I'm going to go and connect it up to some light bulbs. I'm going to make maybe this one here 10 ohms. And maybe another one over here 10 ohms. And I want to take a look and see, what happens with this circuit. Then when we've done that, we can try it again where we say, okay, it's the same 12-volt battery. It has the exact same 2 ohms on the inside, but what if there was just a single light bulb out there of 10 ohms? And we have our 2 ohms on the inside, the internal resistance. For the first circuit, if you take the two 10s and put them together, you reciprocate, add them up, and reciprocate back, two 10s side by side are equivalent to 5. And then that 5 ohms is in series with the 2. So for this circuit here, you've actually got a total resistance of absolutely everything that is 7 ohms. Okay, but later on, if you take a look at this one, for this one the resistance has changed quite a bit. In the after part of the story, the resistance for this one is actually 10 and 2, so this one is 12 ohms. So here's what's happened. It looks like, just kind of speaking generically, and this is the best way to do this, you could say, here's what's going on. When that light bulb was removed, the total resistance has increased. But if the total resistance increases, that could be your kind of first statement. If the total resistance increases, then if you start calculating total currents, now at some point I'm going to stop doing the math, but maybe we could do that with this one. Before you had 12 divided by 7. We had 1.7 amps flowing, and then later we're going to go 12 divided by 12, so that's of course 1. We're going to see that we've got less current coming out of the battery. Okay, no big deal. But then here comes the big deal. Now you have to think about this equation. Well, terminal voltage, which is the voltage that gets to those light bulbs, it's equal to the EMF of your battery minus the I times the R. Now, we never did this in junior science, but now we're ready to talk about it. The EMF doesn't change at all. It's still 12 volts. But the current just went down in the second part of the story. But the internal resistance of 2 ohms stayed the same. So if you stare at that a little bit, you're going to be subtracting a smaller number from your, well, in our case, 12 volts EMF. So you're going to end up overall with a bigger value for the terminal voltage. We're not asking as much from the battery. When there's less flow, we lose less on that inside resistance. So your next sort of statement in terms of principles of physics is that the terminal voltage grows. There's more voltage making it out of the battery. And that is the voltage that's applied to the light bulb. So now all we have to do is say, well, hey, hang on. At the light bulb, the power there would be the voltage that we're getting. It's the terminal voltage actually squared divided by the resistance of the light bulb for that remaining light bulb, that 10 ohms. And if that terminal voltage is going up, but the resistance of the light bulb is staying the same, then you're going to get more power. So that's why it glows more brightly. There's just more power there. So your fourth statement could be, yep, the power in that light bulb because of V squared over R is going to go up. Whenever you're doing those conceptual ones, it's hard. Like I've put the concept stuff there in blue. It's hard to sometimes just lay that out. Just go with numbers. Make up a voltage for your battery. Make up some resistances. Run the numbers so you can see what happens, and then take a step back and talk about what happens just generally. You can say, okay, generally speaking, the total resistance goes up. That means the total current goes down. Hey, we're going to have a better terminal voltage for our battery. That's why the remaining light bulb gets more power. And so there's the end of our 6th unit.